Hi, now let's continue with various GAN architectures, various popular GAN architectures and models. So after the introduction of the generative adversarial networks, DC GANs were proposed, basically scaling up the neural network architecture, proposing some architectural improvements such that they can deliver some quite interesting and visible visual improvements. So as you can see here, this was the main figure, the main pipeline for the architecture of the generative model, where they would have 1004 dimensions of filters, and then followed by 4 deconvolutional steps until the generation of large 64 by 64 image. The results were interesting at the time. Here are some bedroom pictures, and we can see that they all look like they're indeed some form of a bedroom, although it's also quite clear that these are fake images. So while they might be fooling the discriminator of the GAN, to the human eye it is quite obvious that these are not really real pictures. What was very interesting is that this GAN showed you can do vector space arithmetics with the learned codes. So if you were to have pictures with men with glasses, and you subtract the vector of a man and add the vector of a woman, then you would obtain generations. You would obtain a latent code which would yield generations of women with glasses, or with some sort of appearance that looks like wearing glasses. This is a very interesting use case, in fact, because as we said earlier, generative adversarial networks did not really encode data. So how do we know which part of the latent space corresponds to men with glasses or men or women? Well, they in the original work they actually proposed some interesting ways to solve this problem, mainly by manually exploring the latent space and seeing, or clustering these type of appearances to discover these locations where you have this type of semantics. As we discussed earlier, standard generative adversarial networks have a problem with reduced support, and mainly that is because of the KL and or Jensen-Shannon divergence that is implicitly used. So a few years after the original GAN was introduced, Aryovsky, Hintala and Botu introduced the Wasserstein GANs, which replaced the KL and Jensen-Shannon with the Wassersteins, or Earth movers distance. The benefit is that now, even for non-overlapping support regions, we can obtain meaningful distances, and therefore the generator and the discriminator can better optimize the min-max gain required by generative adversarial networks. One of the problems, or one of the characteristics, that's maybe a better word, of generative adversarial networks is that they have no encoder, and therefore it's also not obvious how you can condition the generation on another variable. So the conditional GAN by Mirza and Osendero addresses these specific problems. In fact, they propose to condition on labels. Together with the latent vector, or the noise vector Z, they append a label vector, a one-hot label vector, which indicates which specific label the generative model should generate an image of. So the generative model receives both the Z and Y as input. It returns a generation, which should be relevant for our label Y. And then the discriminator receives both the X and Y now and tries to figure out if this looks correct or not. So for instance, if Y corresponds to a car, then the discriminator should also receive pictures of cars and see whether the real generated image looks like a car or not. Here we see some example tags generated by the algorithm together with images. And after GANs showed so good visual generation results, they were repurposed for all sorts of tasks. Image-to-image translation is a very interesting one, where Isola and others condition GANs on other images, like edge images, and then they can generate actually pictures that would correspond to those conditioned images. Again, here we're conditioning on the edge, so here instead of conditioning on a label vector, we're conditioning on another image. InfoGAN poses the idea that our noise variables should somehow be disentangled, should be somehow carrying distinct type of features or informations per dimension or per subsets of dimensions. So the InfoGAN method proposes to add a mutual information term as regularization on top of the min-max constraint. And basically the intuition is to require high mutual information between our code, latent code C, which captures sort of semantics with the actual generation. By making sure that we have high mutual information between our latent code C and our generation, we make sure that we're not going to learn trivial codes for C. So we're not going to have the latent vector ignored. As mutual information is actually a quantity that requires the estimation of the posterior, the true posterior, the paper relies on a variational approximation to do the learning. CycleGAN is improvement in a way of the image-to-image translation task, where the basic idea is to have two domains, d of x and d of y, and then from x we move to y, so we generate images from x, for domain x we generate images that belong to domain y, and our discriminator has, our dy discriminator has to be full that way. But then again, we are closing the loop by using this y generations our input to return back to our domain x. And by doing so, we are closing the circle. Additionally, we can consider the cycle constraints that our back generated x should be as close as possible to the original x itself. And by making sure that these are close, we can have stronger constraints and more robust learning. The results for CycleGAN are very interesting. So if our input is horses, we can paint it to look like zebras. Last, StyleGAN was proposed last year by NVIDIA, mainly proposing architectural innovations and ways we can scale up the architecture and using images of high resolution and therefore also outputs of high resolution. They were able to obtain impressive generations, as you can see in this picture, and as I showed you in the pictures before. So this shows the potential that GANs have in generating realistic or real-like samples. So today we discussed what is the motivation behind implicit density functions, and we gave a short introduction to generative adversarial networks. We discussed some of the challenges that we face when working with GANs, and we presented some of the most popular GAN variants and models out there, some of them producing really impressive and high quality results. Thank you.